Hi, everyone. So today I will be talking about forecasting with machine learning. Now, if you're like me, when you see this title, you think buzzword, buzzword. That was my first thought as well. And I think that's kind of the point of today's talk. And the idea that we always talk about forecasting and we always talk about machine learning. But what exactly does that mean? How do we do it? What are the advantages? And what does that really mean? So when I first thought of forecasting, I always thought about the weather. And that is an example of a forecasting question, right? So this is something that we think about all the time. How much snow is going to happen, right? And that's something we need to plan around, especially in this area. But there's other things too that we have to rely on forecasting for. For example, we might be looking at collisions, things that might matter a whole lot for different people in different fields. It could be something that is relevant for finance, especially right now in terms of the markets. Maybe that's something that's extremely pressing for a lot of people to kind of understand what are those future values going to look like. Of course, it could be the state of the world, and it could just be the big thing that we don't want to talk about anymore, which is COVID. So the point here is that forecasting is used everywhere. All throughout your life, you see it. You probably don't even realize it anymore when you think about the fact that you're trying to understand what the future is. You probably do it in your head all the time too, without machine learning models. But the idea is, how can we do it in a more rigorous way? Before we get to that, though, I guess the main question is, why are we here? So why is this important? And these are just 5 particular reasons, broad umbrella groups of reasons why we actually care about this issue. So like we talked about before, you might be able to anticipate demand. Maybe you're talking about demand in terms of personnel, labor, or you're talking about actual parts and component parts. Maybe you're able to reduce costs, and those kinds of things can make a huge difference. Prepare safeguards, right? You want to make sure you understand what's coming so that you're ready to handle that when it happens. Assessing risk, and that's, it goes along with everything we're talking about, understanding what you're expecting to see, how you can prepare for it, and how to quantify that. And then of course the big one here, which is save lives. And yeah, forecasting can save lives if you do it well. Of course, on the same vein, if you don't do it well and if you make mistakes, it can have the adverse effect. But of course, there are huge advantages with forecasting. So with that, now that we've kind of motivated today's talk, let's talk about kind of how we're actually going to talk about it. So first, again, let's define forecasting so that we're all kind of on the same page. We'll explain how we do it with machine learning, how we do it without machine learning currently. And then we'll talk a little bit more about how we specifically apply machine learning to forecasting. So the idea there is kind of what are the pros, what are the cons, and how can we use machine learning to address a lot of questions that we all may have when approaching these questions. And then finally, we're going to conclude with a particular case study where we actually try this out. This is a project that I've worked on here at IDA. And so we'll be able to look at a few cool graphs and numbers. So first, what is forecasting? Like I said, it's a buzzword. So let's just make sure we're all on the same page in terms of what we're talking about. So here we'll use a very simple definition, which is just basically predicting future values. And so that's kind of the idea that we're going to take throughout today's conversation. And the idea behind this is that if you're talking about predicting future values, there has to be some kind of temporal component to the data. So that doesn't necessarily mean to be a well-defined time period 1, time period 2, time period 3, but there needs to be an underlying data structure that reveals itself to be of the time series nature. And much like Alan talked about in the talk beforehand, forecasting, there still are like many implications that you have to consider when you're talking about policy analysis, when you're talking about causal analysis. And so he's talked about this a whole lot, so I'm not going to go into this really that much. There are a lot of papers on this, very much on this subject in particular. So if it is something of interest, I encourage you to look more into that. And again, like we were talking about before, there are a lot of applications of forecasting. I know the one example we're talking about today is with personnel, but of course there's no requirement that you use personnel data to forecast. So these are just some examples. I'm not going to read them out loud. Some are of great personal importance, right? Which is like, when should I buy the plane tickets and what will gas prices be next month? And others are of more of an institutional standpoint. So of course, there are a lot of advantages here. So the way the forecasting is currently done is in a wide range of different ways. Now, I want to preface this slide by saying that the position of these specific models, don't read into it too carefully. It's more designed for illustrative purposes only, but it shows that there's a wide range of how we do it. So on the left-hand side, you see parametric models. So those are models where we give them a very clear, either we give them a specification or there is a specification that's learned, and we can kind of say, okay, this is the parameter. This had this much of an effect. And you see what's on that side. But on the other side, and that's kind of like the neural network side, that's the non-parametric. And that is, that the model is kind of learning from the data. That's more of a black box. There is no, direct specification. And we use a wide variety of tools that range across the spectrum. So the idea there is just kind of, there are many ways of doing this. We're not going to talk about all of these, but there are a lot of ways of doing this. But with a lot of these ways, there are a lot of problems that some methods address really well, some don't address at all, and so on. So that kind of brings us to the question of, sometimes we run into problems where we're just like, we don't know what to do. And that happens a lot with forecasting. It happens to me all the time with forecasting. And these are just 4 examples of questions that we might have all the time, right? So maybe you have way too many, covariates. Maybe you have a feature space of, you have 2,000, daily telemetry readings. Well, I mean, what are you supposed to do with that, right? Like you can't put that all into a model, or maybe you can. But at the same time, like what happens if there's 2 features that are correlated? What happens if you have an interaction? Are you supposed to just go through and hard code all those? That doesn't really make a lot of sense. What happens if you want some uncertainty? You say, I don't want just a point estimate. I want to understand what's the range it's going to fall into. Well, some methods are great at that. Some are horrible at that. And then, of course, the other 2, which is that my models train well, don't extrapolate well. That's the big problem there. You built a great model, it means nothing. And then the data distribution, and that's probably the biggest one that we'll talk about today in terms of, that one's a really tricky problem. But again, it's a problem that a lot of us face, especially when we're talking about forecasting, where we do see that temporal distribution shift. So how does ML fit into this picture? How does it take those 4 issues and how does it address those? So if we're talking about model selection and overfitting, there's a lot of tools built into machine learning that we can use and we can leverage to kind of address this problem. So with regularization, we can try to say, in terms of that bias variance trade-off, we're going to aim for a little bit more of understanding the data, a little bit more bias, so that we can kind of understand that we're not going to overfit the data. It's not going to be a perfect model, but it may extrapolate very well. And so on, we might be able to use, why use one decision tree? Why not use a random forest and that kind of idea, right? Why not use an ensemble model? Why not take 100 models, throw them all together and have them vote? And these are all things that people do. It happens all the time. And these are great tools for that reason. Again, like we were talking about, you have 1,000, 2,000 features. What are you supposed to do with them? You can use dimensionality reduction techniques. So you can use factor analysis, PCA. You can use a wide variety of tools, turn that feature space into something more usable. But, again, like, are you supposed to hard code all the interactions? Are you supposed to go through and say feature 1 times feature 2, and so on? Well, no, some models may automatically kind of pick up on those behavior patterns on their own. And that's something that's huge with machine learning, in particular, the fact that, it allows you to be a little bit lazy. And I think that's kind of huge when you're building out large scale models. With forecast uncertainty, there is a lot of room for understanding, what is the prediction interval here? What am I looking at? If I'm saying that this value, the gas prices next month are going to be $5, am I talking $5, and in 1 cent on the top end and $4.99 on the bottom end? Or am I talking, it could be anywhere between 0 and 100? And that's kind of a key question because that really means something completely different. And then, of course, distribution drift, which I said kind of is a tricky one, and it does depend on the situation. But there are various different ways of addressing this problem within machine learning, and one of those ways, kind of depends on how you set up your problem. So how you set up the training and testing data, and how you evaluate the model. So with that, I kind of want to talk about how you split up the model, right? So how do you split up your training data, your testing data, where the testing data is used for evaluation purposes and the training data is used to actually build the model. So there's 2 different ways we're going to talk about here. If you look at the left-hand side, this is a panel data set. It's indexed by individuals, and let's assume that actually it's not panel here, but let's assume it is, right? Where you have individuals over time. You can split by individuals, and so you can say, that I take 70% of my individuals observed over 20 years, and I throw them into bucket 1. They're my training set. I'm going to hold out 30% of those individuals and test on them, and that's a perfectly fine way of doing it. That's it's very conventional in terms of just kind of slowing it down by the observations, or in this case, the individuals. The trick there is that you are picking up on a lot of that historical contours. So when we're talking about distribution shift and we're talking about, let's say, non-stationarity, this model is going to start evaluating itself against a model that's been able to learn all those trends. And so that's one interesting caveat there. Is it good? Is it bad? I don't know. That's a judgment call. Probably not great. But again, that's for you a decision to make in the moment. On the other hand, you can split the sample over time periods. So you can say, if I have 20 years, I'm going to use up until year 15 to train my model, and then I'll hold out the last 5 years and predict on those and see how I do. This is a lot more realistic, right? This kind of answers the question, how would I have done X years ago? And so that makes it very valuable. But again, you're not picking up on those historical contours. So there is a huge trade-off there. Additionally, you're only using data up until X years ago. So if some of your key data is happening right now, you're missing out on that. You're not being able to use it. Whereas in option one, you are able to use it. So both of these have and the reason why distribution drift kind of depends on the situation is that both of these cause a very different issue with distribution drift. And again, it depends on the feature space as well. So with that, I kind of want to transition to a little bit of what we've done here in terms of forecasting, and that is we've actually built a Python package called the Finite Interval Forecasting Engine, which many of the team members here have worked on. And the idea there is to use machine learning to forecast future values. So very topical, very powerful, and it's all open source on Python. The idea is that you can use Phi for survival analysis, which was its main function. So to say, what's the probability that an individual or an entity remains in this data set X periods from now, or X plus 1 periods from now. And it does that by kind of creating an individual prediction window. It's a binary classification task on each time interval. However, you can also do it you can also use Phi to predict future values. So let's say you had a list of gas prices and you said, okay, what are gas prices? You can use Phi to do that. And that's kind of why it's so valuable. It's a great tool and it has a lot of customizability. So the only reason I'm talking about this, I'm not trying to sell you on it. The only reason I'm talking about it is because we actually use this for the case study today. And so I want to kind of give you that background so we can kind of dive more into that. So with that, let's dive more into it. The idea is that the Air National Guard had asked our team to predict the number of school slots that they would need for their occupations for each year moving forward. So, for a particular school slot, how many people do they need? How many people should they have school slots for? The problem is that how do you do that? Well, you can use the idea of, if someone leaves, that means they've left a spot. And if they've left a spot, that means someone else needs to be trained to fill that spot so that when they leave, they are ready to go. But the counterpoint is that, maybe that's not the only way that demand is generated. So this is kind of the way that we looked at this task. And so I'm going to talk about the first phase of our modeling approach, which was simply just, can we predict who's exiting so that we can fill that first component of demand. The actual model in the paper does take a second approach to figure out what are the other sources of demand generation. But of course, for this particular conference, we're only going to talk about the RPM, which is the retention prediction model, which is forecasting. So in order to do so, we actually used a gradient boosted tree model. This is one of my favorites. I think this is one of a lot of people's favorites because it does really well. In fact, as the lead developer for Finite points out, it usually wins most of the Kaggle competitions. So it's lighter than neural networks and it's fantastic. So that's what we use here. And we do that to predict 5-year intervals and 5-year predictions for whether someone's going to exit service. So in order to test this, we actually chose option 2 in the splitting data. We chose to train up until 2016 to test on those 5 years and then eventually forecast on the most recent data to provide our estimates. In order to evaluate our performance, we looked at precision and recall in particular. And the reason why we did that is because there's a large amount of class imbalance. And again, this is another reason why machine learning has advantages when it comes to forecasting, because you can use these calibration techniques that are designed for it that really help to get at the heart of the matter. So in terms of how we actually did, that's 76.7% of all exit survival observations across 5 years. That's accuracy, and that's misleading. Because the idea is that if you just said that everyone stayed, you would probably get like 75% accuracy. And in this case, it's actually, you would get 76.6%. So yeah, it doesn't seem like you did a good job. But of course, that model doesn't tell you anything. So we look at precision and recall, and we see that if we predict someone to exit, there is a 51.8% chance that they will exit. And all the people that did exit, we identified about 70%. So that's pretty good. And I kind of want to dive into that a little bit more carefully. But before we do that, I did talk about how gradient boosted trees were my favorite model and how they're great. But I understand that this room is probably a mix of people. So let's go into gradient boosted trees and kind of talk about why they're really great. And then maybe this will kind of help us understand some of the problems that we might run into with this particular model type. So random forest is on the bottom right there. And I want to draw your attention to that right away, because when we think about an ensemble tree model, this is what we think of, right? We think of, why not just take a collection of trees, throw them all together, and then just have it work? Why do we need to have a gradient boosted tree model? And the idea there is because random forests, they build a collection of independent trees. But gradient boosted trees say, I'm going to do my first one. Okay, what did I mess up? Let me focus on those, try to get those right. Okay, let me do that again. And so every single time you're focusing on the residual and you're trying to make that better, And what that does is it actually lends itself really well to class imbalance. And so it's a perfect model for this particular case because it's able to kind of hone in on what it's missing and to get that done right. And then of course you can set hyperparameters. So these might, match a lot of what you see in traditional gradient boosted tree models, but we use the light GBM implementation, so they're slightly different. But the idea there is you can say, how deep is my tree? How many trees do I have? At what point am I going to say, you know what, this isn't working anymore, I'm just going to cut it off? And those are all things you can set. You can optimize your hyperparameter space, which is a really cool, area of research. And again, another advantage of using machine learning here. So with that, what does our problem look like, right? We talked about how we're using a gradient boosted tree, but what does the feature space look like? Well, we have 638 features. So, talk about a lot of features, right? And this is an example where we don't have to predefine the interactions. So we use a wide variety of personnel data on people's lives. The idea is that what makes you more likely to leave service? Maybe you just had a kid and you're about to deploy. That's not really a great situation to be in. Maybe that is something that would cause you to leave service. And that is something that we can kind of replicate in our data set by understanding, the tree model is going to pick up on those splits. So as long as we give them information about the deployment schedule and we give them information about how long it's been since you've had a kid, it should be able to figure out those contours. So again, we use a wide variety of data here. I'll let you read it for yourself. And we train it, again, like I was saying before, on various different periods. We do build a different forecasting model and an evaluation model. The idea is that the forecasting model is the one that we use to give the actual results, and that trains all the way up until the final period. These are only two different models because of the underlying data, but in reality, they're essentially the same thing. They use the exact same feature space and the same type of model. So here's the question, right? Which is, how do we do? So we're going to look at a visual confusion matrix. Rather than looking at, a 2x2 grid, I thought it would be a whole lot more fun to look at the distribution of probabilities. So on the top here, you see the people who've actually exited over a 5-year window. And on the bottom, the people who've actually stayed. So those are the people who continue to stay in service the following year. The top looks pretty bad, and the bottom looks fantastic, right? So the bottom is that we've predicted that the probability of those who actually have stayed is going to be really high. So that's exactly what you want it to look like. But the top is a bell curve and it's not centered around 0, which is what it should be. So what happened, right? The question then is, why are you so good at predicting stays and you are so bad at predicting exits? Is it class imbalance or is it something else? Well, the leading theory here is that we can tell you when someone's about to stay. We can tell you, hey, they just completed a training course. So they're probably going to stay to use that. But if they did not use the training course, if they did not take it, does that mean they're more likely to exit? No, it just means nothing. And that's kind of the key here. We have a lot of drivers of retention, and we don't have a lot of drivers of attrition. And so that's something that, if this project was to continue onwards, that's an area of exploration. It's kind of how can we get better data? And how can we make sure our model's tuned to that to make sure that we can kind of figure that out? The reason I want to spend so much time on that feature engineering piece is because that's a huge part of machine learning. And it's sometimes where you can get the biggest difference in terms of performance. So the key here, though, is the red line, right? And so that red line is designed with a precision recall framework in mind. So we've maximized basically the two questions, right? Which is, what's the probability you've exited if I have said you've exited, and how many of the total exits did I predict? And we're trying to maximize those two with the harmonic mean. That red line is that point which does it. That's the threshold. But the question is, if this is the confusion matrix, where you have the top left as your true exits and the bottom right as your true stays, what if we shift that red line, right? Oh, sorry. I got a little ahead of myself. What if we shift the red line? And that is kind of the question, which is here. And so you can see that, and I'm going to go back just so we can see it real quick, that before we were looking at false stays on the top right, false exits on the top or on the bottom left, but now those have changed in size. So we have, we have a lot less false exits and we have a lot more false stays. So the idea there is you can kind of pick that depending on your own task. And you can say, what do I want to do? Is it more costly to say that if I predicted correctly, or if I predicted incorrectly and I've said that someone is going to exit, but they didn't, then, I need to prioritize that or vice versa. And so with that, I kind of want to return to the general idea of this presentation, which is that forecasting is very important. Again, you see it everywhere, and machine learning fits into that so clearly. So I'll let you sit with these 5. The key here is that machine learning can help with all of these. So with that, thank you very much. I really appreciate it.
I'll take a couple minutes to ask questions. How much better is your model at predicting, the outcomes than say like, just a human doing it, previously saying like, oh, well, I think this number of people are going to leave. Does it do better than just people were trying to forecast these?
Yeah.
By how much?
So that's a great question. I appreciate the setup for that actually, because that's something that we took a look at, right? And that's a great point, which is that you have to have a baseline, right? So understanding this is how people do right now. Because if you're not doing any better, then there's no point. Your model's garbage. In this particular case, people are horrible at predicting retention and exits for the Air National Guard. We asked them how they did it. The methodology seems a little more unclear, and it seems a lot more just based on heuristics of like, we typically lose this amount per year, right? But they can't look at some of the fidelity data that we did. So that number is 70%. We do 70% better than what they do. In an average year, we have about 7% error, and they have, I believe it is a lot higher than that. So the purpose of this model is to make a huge impact. It's not going to be perfect. As you saw, it's not perfect by any means, but it's a whole lot better.
Yeah, I guess, and I think that kind of goes to like a larger point in that, I think a lot of people harp on, a model being wrong, but it just, and not, look, this is better than what you did. You guys are not doing such a great job of predicting. Is this right? No, but it's certainly not better.
Absolutely. I think, and just to quickly add on that, if you aim for 100% accuracy, you're doing something wrong, right? Every problem's got a cap. You just got to figure out how close you can get to the cap. But yeah, in the back. Sorry. Yes.
I guess it gets into the idea of operator trust and that sort of thing. Would this be better than to use as more of a influence on decision rather than a determinant of the decision?
Yeah, so that is definitely a question for, I would say, like whoever is using these. I would personally say that it's probably better to use it as a tool to say that I'm not going to make my decision based off of this, but if someone has a 50% chance of exiting or staying, maybe I'll have a conversation with them. I'm not going to do something based off of that. So I would agree that in this particular task, when you're talking about school slot forecasting, you have this number that it gives you. I know I need 12 slots, but you also know whatever you know because you're in the job. And so I think you have to use them all together and say, this is a tool, it is not the answer. But yeah.
Or in the case of loading the dice rather than rolling them.
Yeah.
To put it in a bad example.
Do you have a question here? Yeah.
Yeah, I was going to ask, were you able to do like any analysis, like once you actually create the model, analysis of factors that actually influence the model? And I know you talked a little bit about interactions, like were you also able to look at any interactions between factors that influence the model?
Yeah, so this is a great question, and kind of goes to that causal point that I mentioned earlier, which is you have to be really careful because our feature space is horribly messy and collinear, right? So when we're looking at a particular feature, it may be that there's 5 features that all represent the same thing that are all at the bottom of feature importances. We actually did take a look at this, with the caveat that we were only looking at it to see what's being split on and what is relevant to the model. And training was huge. So whether someone took a training, and that's why I used that in the example, and activations for the Air National Guard were huge. One theory that I had originally was that traumatic event exposure was going to be a huge factor, and it was going to be something where, if there were a lot of casualties in your unit, maybe you wouldn't want to come back. But no, not at all. Actually, I don't think the model's put on that at all. So the key there is that if we cleaned up that feature space, we might be able to understand what is the true impact of that, but even still, probably a little bit hard to say. Yeah. Yes.
When you were studying your data, you can split by population, you can split by years. I understand how that, partially gets into questions of the drift in your distribution. It doesn't get into questions about changing factors over time. And in fact, you're talking about using data from 2014 to predict what's happening right at the beginning of COVID. I expect some of those decisions that people are making based on different factors. Can you speak a little bit to how you might address that?
Yeah, that's a great question. So one thing in particular with gradient boosted tree models, and perhaps one of the biggest limitations, is that it does a horrible job of addressing non-stationarity, and that's because it's not meant for trends. And so the question then is kind of how do you address that? How do you figure out how to take your trends and pull them out, pull out the relevant information? So we have a lot of time series like lagged features in the sense of that. But more so than that, it's kind of the idea that if a pandemic happens, right? And there's not really a way that we can predict that. Well, we can try to understand what is going on during that pandemic that's affecting people's behavior. Because it's not that it's just a pandemic. That doesn't mean anything. Is it that people are staying home more, right? Or is it that, and I'm speaking more generally now, is it that people are staying home more? Is it that the unemployment rate is higher? Is it that, there's no toilet paper in the stores? Like those are the relevant features. It's not that a pandemic happened. And so if you had those features reported the entire time, and you had a model that was able to handle values that were slightly outside of what it's seen before, then you should theoretically be able to handle it. In our particular case, we did not do a great job with that. Yes.
So kind of following up on that a little bit, I have a question about how do we evaluate forecasting models? In particular, when they're forecasting models about something like a pandemic. So there's a forecast, there's a pandemic, right? If we don't do anything, millions of people will die. You should all wear masks and socially distance.
Right.
People socially distance and wear masks. The actual number of deaths is much lower than predicted. People say, oh my God, you over predicted, your model's terrible. This is nearly as, you don't know what you're doing, right? So how do you evaluate models in a real life context when that's what you're dealing with?
Yeah, I mean, it's also a very good point because as soon as someone starts acting on these forecasts, right, then you've got a problem because all your forecasts are completely thrown out in terms of the value, right? They're still usable, but they've changed their entire feature space. Yeah, I mean, I think it's a really good question. You can argue that your probabilities are, relative. So if someone is more likely to exit than another person, maybe that directionality still holds, and maybe you have a metric space that is still kind of linear in that direction. But maybe you can't, maybe that doesn't hold true. And these are all really good points that, and I know you're going to talk a little bit about something related to this. So I know that that's really relevant. But if you're trying to understand, what would this have been if this policy didn't have happened? What didn't happen, then that is a question for a different type of model, which I'm sure you're probably an expert on. Yeah, any other questions? Great, yeah, thank you guys so much. This was really fun.